Okay, so the least squares problem that we have been looking at was this problem, right? So you have to minimize for x in Rn norm of ax minus b whole square, right? So this was the least squares problem. This was the least squares problem that we were basically addressing, right? And based on whether the b is a vector in Rn Rm and A is a vector in R matrix in A M cross N. Based on the type of this B, whether it is having real values or it has labels. Based on that, we kind of saw the applications in data fitting, and we saw another application in classification, right? So least squares classification and least squares data fitting based on what are the types of outputs y you see, right? So basically this was the least squares problem that we saw, and we had seen that when A is full column rank, A is full column rank matrix, then what happens? In case of A being full column rank, we have seen that the solution X will be given as A transpose A inverse A transpose B, right? And this particular matrix is called as pseudo inverse. So this is what we have already seen. So now what we really want to do today, like there are more than one objective functions, right? So this particular function is called as objective function, right? So this is the objective function. And what do we want to do? We want to minimize this objective function with respect to the variable x, right? So we are trying to minimize this objective function with respect to x. Now in multi-objective least squares problem, the question that is being asked to us is that there are more than one objective functions, okay? More than one objective functions, and you want to simultaneously minimize those with respect to the same x. That's what we want to do, right? So in multi-objective, what we are doing, multiple objective functions. Okay, so multiple objective functions is what we are given. So what are those multiple objective functions? Let us write down. Okay, so J1 is this A1x minus B1 whole square. J2 is this A2x minus B2 whole square, and so on and so forth. The kth objective Jk is basically Akx minus Bk whole square. Okay, so this is the objective. This is the objectives. Okay, 1, 2, 3 that are given to us. Then Ai are the matrices which belong to Mi cross n, and these vectors Bi are actually the vectors in Mi, right? So that is what we have for I is equal to 1 2 up to k. And what do we seek? We seek a common solution. Okay, we seek a common solution x hat. We seek a common solution x hat belonging to Rn that will kind of give a compromise. Okay, that will kind of minimize all these functions j1 j2 jk, okay, together simultaneously, not one by one. One by one, if it has to satisfy, then we all know that x hat will be the solution of this particular type, right? So x hat will be a solution of this particular type provided that the column of ai is minimum. But this particular solution x hat may not be the least square solution considering this cost function, right? It may be the least square solution of this, but it may not be the least square solution of this. So now one individual least square solutions for J1, J2, Jk that you may find out may not be the minimizing solutions of the other cost functions. It is clear. And because of that, now we want to have a we want to have a common solution x hat, which will kind of have a compromise, and it will decrease values of all these cost functions j1, j2, jk together. Okay, so that is what we really want to do. So multi-objective, multi-criteria, the name comes because the objective is like there are k simultaneous objectives that we have j1, j2, jk, and we want x hat a common solution which will have a compromise and it will kind of force all the cost functions to go down simultaneously. Okay, so that is what this problem is. And how do we handle this? Via least squares. uh, so what we will do is multi-objective uh, weighted sum. Okay, so multi-objective least squares via weighted sum. So what I
Sir,
will do is,
Bharat here.
yeah,
Sir, just one question. So in this different functions, right, J1, J2, and Jk.
yeah.
So for example, when you say J2 is equal to A2x minus B2, A2 is the coefficient of the second row, right? Or is it something different?
No, no. So like here you have matrix, no? So matrix A is like this, then X is like this, and B is like this,
Correct.
correct? So this is my AX is equal to B in general. And what you are trying to do is you are trying to do AX minus B. This you are trying to minimize with
Correct.
respect to X in Rn, right? So
Correct.
consider there are K problems simultaneously. AIK is equal to BI. There are K such problems simultaneously you are looking at. So there are K such things simultaneously and the solution X should be common to all of them. Now that is a difficulty that you will have, no? Like for one problem, J1, you are looking at A1x minus B1. That is what you are looking
So
at.
my confusion here is whenever we get a data set, I mean, let's say it has some 2000 rows, and you have some four dependent variables, and so in this case, what will be AI? I mean, is it a row indicator
No,
what?
no, we have not yet come to the rows and columns. I am not even
Okay.
talking of data. I'm just saying that you have these problems. So we'll come to a place where we will see when we get data what type of multi-objective least squares problems we are talking about. Okay.
Okay.
So right now I am just saying that you have such several problems. Is that part clear to you? We are not coming to data yet.
Okay. Fine,
So
because
is
I
this
was
no,
trying to
no,
compare
data,
this with the
no,
data.
no, data connection I will give you later. But right now we first want to understand what we are going to do. So
Okay.
is this part clear to you? Like the problem is clear. Don't worry about data. We'll
Okay.
see it later.
Okay.
Sir,
Yes.
in this, all the AIs have the same number of columns,
Yeah.
right? So why can't we stack them one by one and then just do AX minus B and optimize that?
So we'll see how. So what you are saying is something that is what precisely we are doing. But at the same time, yeah, we'll do that. So that is what I'm going to do through this weighted sum. What you are saying.
Yes, sir.
Okay, so what I'm going to do now is I'm going to write down a new objective J, which is basically the weighted sum of these objectives. Okay, lambda 1 J1 plus lambda 2 J2 plus lambda k Jk. Okay, that is what I'm going to do. And I'm going to take these lambdas to be positive, of course. So lambda 1, lambda 2 are the weights which are all positives. And in particular, when I take lambda 1, lambda 2 up to lambda k, all of them to be equal to 1, then I'm just summing up all the cost functions together, right? So my j is basically lambda 1 into a1x minus b1 whole square plus lambda 2 into a2x minus b2 whole square, so on and so forth, lambda k into ak minus akx minus bk whole square, right? So that is what I have. And how do I choose these weights lambda? How do I choose these weights lambda is really something that is critical. So there are various ways in which one can choose weights lambda based on again your experience with what type of problem you are trying to solve and so on and so forth. You can take all the lambda is to be equal to 1 also, it doesn't matter. But roughly, when you have these lambda 1, lambda 2, suppose I compare this lambda 1 and lambda 2, suppose lambda 1 is 2 times bigger than lambda 2. Lambda 1 is 2 times bigger than lambda 2. Then what I am really saying is that I care that this guy goes to 0, J1 goes to 0 faster than this J2. And how? 2 times. Okay, so my concern about J1 going to 0 is twice as much as my concern that J2 is going to 0. So when I'm trying to find out common solution, all the values of J1, J2, Jk, I am trying to push towards 0, right? I am trying to minimize all the values of this J1, J2, Jk simultaneously. But while I am pushing those values to a minimum value, I am reducing those values. My concern about J1 reducing is more than the concern. I don't really care if J2 goes to 0. How much? By the factor 2 times. Okay, so that is what I really mean. So if you have some such criteria in your mind, if you have some such criteria in your mind about the particular problem, you can choose your weights lambda 1, lambda 2, lambda k in such a way that you give importance to some particular cost functions j1, j2, jk amongst these, and you do not give much importance to some other cost functions, like they are little less important than the other cost functions, right? So these values of lambda I actually are chosen based on these type of understandings. Okay, so that is what typically is done. And once you have this cost function, and then I think it is easy to see, right? So what we will do basically is we will do something that Aditya suggested, right? So what we have this j, and this j once again I'll write down here so that it is clear. So j is basically lambda 1 a1 x minus b1 whole square plus lambda 2 a2 x minus b2 whole square, and so on so forth. Lambda k into akx minus bk whole square, right? So that is what I have as my j cost function. And what I want to do, I want to minimize this j with respect to x in Rn, right? That is what I want to do. So if I have to do that, then you see this j the way I have written it. Do you all agree that this j can be written in this particular way? So I'm looking at a vector, and the vector is basically this root of lambda 1 into a1x minus b1. Okay, that's the vector. Then root of lambda 2 a2x minus b2. That's the vector. And root of lambda k amk minus bk. And I am looking at the 2 norm square. Okay, just give me a minute. Someone is at the door. Okay, just give me. Yeah, sorry about the interruption, but yeah, this is what you have, right? So do you all agree that this cost function can be written in this way? So this big vector that is sitting inside here is actually a vector of the size m cross 1, where the m is actually m1 plus m2 plus mk. Do you all agree that this is what it is? And if I look at the 2 norm square of this vector, I'll basically get what j is. I hope you can see this fact, right? And then once you understand this, then what is this j? Then this j basically is this vector. Then I can write down this as root of lambda 1 a1, lambda 2 a2, lambda k ak, multiplying x minus b1 b2 up to bk. Correct? And if I can write this down, this is basically equal to a tilde x minus b tilde And what is this A tilde and B tilde? A tilde and B tilde are obviously these matrices, right? So A tilde matrix is basically this matrix. And what is the B tilde vector? B tilde vector is basically this vector, right? You do the concatenated versions of this, and this is what you'll get as A tilde, B tilde. And I think this is what Aditya you were referring to.
Yes,
Did
sir.
you mean this? Okay, so this
But I
is
didn't
what.
consider this lambda factor.
Yeah, so lambda factor is typically done based on how important it is for you to force value of a particular J1 to the minimum value or to zero, as close to zero as possible compared to the other cost functions. Right? Based on that, you will design these weights lambda 1, lambda 2, lambda k. Okay, that
So
is
even B1, B2 should be multiplied by lambda.
what is that?
B1, B2, Bk also should be multiplied by lambda I, right?
Why? Oh, sorry. In this vector bk. Okay,
Yes.
sorry. Yeah. In the vector bk, you are right. So here also you have to multiply them by lambda 1, lambda 2, and lambda k. You are right. Sorry. So this is what you'll get. A tilde x is equal to b tilde, and m is equal to basically the sum m1 plus m2 plus mk. So you can call this a tilde to be a matrix in m cross n, and b tilde to be the matrix in m cross 1, right? So Rn basically that is what you have, and M is basically the sum m1 m2 mk. And now if the columns of this matrix A tilde, so now if the columns of this matrix A tilde are linearly independent, columns of A tilde are linearly independent. Okay, columns of A tilde are linearly independent. Then what is the least square solution? Then the least square solution is given by, we all know, using the normal equation. So the least square solution x hat will be given by A tilde transpose A tilde inverse A tilde transpose B tilde, correct? So that is what you will get. And what is A tilde transpose A tilde? So A tilde, if I write down basically as square root of lambda 1 into A1, square root of lambda 2 into A2, so on and so forth, square root of lambda k into AK, right? So suppose this is my A tilde. Then do you agree that A tilde transpose A tilde is basically lambda 1 A1 transpose A1 plus lambda 2 A2 transpose A2 plus so on and so forth plus lambda k AK transpose AK. This is what A transpose tilde A tilde transpose A tilde will be equal to. And similarly, you can see what is A tilde transpose B tilde, that A tilde transpose B tilde. Similarly, this term also you can see is basically lambda 1 into A1 transpose B1 plus lambda 2 into A2 transpose B2. And then you can see that x hat is basically nothing but lambda 1 A1 tilde, A1 transpose A1, lambda 1 into A1 transpose A1 plus lambda 2 into A2 transpose A2 plus so on and so forth, lambda k into AK transpose AK, and you are taking inverse of this into lambda 1 A1 transpose B1, so on and so forth, plus lambda k AK transpose BK. Do you all agree that this is how x hat really looks like? So what you really are doing is you are having all these gram matrices together, right? So if you call gi to be ai transpose ai, then you have all these gram matrices, in fact weighted gram matrices, right? Lambda 1 lambda I gi, you are looking at those weighted gram matrices and you are taking inverse of those weighted gram matrices, and up on top of it you have that lambda 1 a1 transpose b1, obviously that part getting multiplied, right? So this is something that looks very similar, closely related to what we were really doing. So simultaneously several least squares objective functions you have to minimize, and you have to minimize with respect to that common x. So you need a common solution to all the problems, right? So when you are trying to have common solution, you have to have these type of things. Okay, so in particular what we can do is we can look at case when k is equal to 2. case of k is equal to 2, right? So there are only two objectives, J1 and J2, and you are trying to simultaneously minimize J1 and J2 with respect to k. So J is actually equal to lambda 1 J1 plus lambda 2 J2. So you can actually write this down as J1 plus lambda J2 for lambda equal to lambda 2 by lambda 1. Okay, say for example. So in this particular case, what it really means, so this is like by criteria problem or by objective. Okay, by objective. Instead of multi-objective, this is by objective. Okay, and this is kind of called as primary objective. Okay, so this is something which is called as primary objective. So you want this to go to 0, and this is your secondary objective, and based on value of lambda, so typically this value of lambda will be less than 1. So your first important task is to force that J1 to go to 0, and the secondary task is to force J2 also to go to 0, or its minimum value, right? Minimum value as much as possible. That is what you are really trying to do. And these are the type of things that you will really see. Okay, so I'll consider a couple of examples where these things really come into the picture, and when I will talk of these examples, then we will see how these things really fit in. Okay, so one of the important problems is a problem which is oftentimes called as estimation problem or inversion problem. Okay, so one of the let me write this down properly. So applications of multi-objective. Okay, so the important problem is the problem of estimation, or it is called as inversion. Okay, so this estimation problem is also called as inversion problem, and let us see what this problem really is. Okay, so I'll write down this problem as y is equal to ax plus some vector epsilon. Okay, so I'll write this problem as ax plus epsilon, and I have no so in particular, if epsilon were equal to 0, okay, in particular, if epsilon were equal to 0, then what we really have here is y is equal to ax, and if you cannot find out x exactly, then you will do the least squares problem and try to find out the least square solution, provided that the columns of A are linearly independent. This is something that we have already seen. Okay, but now what we don't know is what is this epsilon. Okay, so this epsilon is basically the measurement error in y. Okay, so this measurement error in y is actually unknown. We don't know this measurement error in y. Also, there are no constraints on x. Okay, no constraints on x. No constraints on no constraints on A. So A can be a tall matrix, it can be a square matrix, it can be a wide matrix, A can be anything. It may be full rank, it may not be full rank. If it is full rank, then we know what is the solution. If epsilon is equal to 0, we know what is the solution. But otherwise, this solution is not known. So this problem is called as estimation problem. So what happens in real life situation is you always observe these y values. Okay, so these y values are measurement values, and you know y is related to x. You know y is related to x through some functional relationship. The functional relationship that we are talking of here is the linear relationship which is given by this matrix A. So this functional relationship between y and x is known to you. The thing is that you have no means to measure x. So you want to measure x, or you want to estimate x through the measurements of y, right? So that is what will be happening in real life. So y measurements are known. Y measurements, when you measure, the measuring might have some measurement errors. Okay, so those measurement errors are stored in epsilon. So those measurement errors are typically not known. They are random in nature, but they are small. The assumption is that you will have measurement errors, but those measurements error will be small. Okay, so this is the general setting. This is the general setting. And in that particular setting, as we discussed, if epsilon is equal to 0, A has full column rank, then we have the exact inversion, right? We have the exact relationship. We know what exactly X will be. It will be pseudo inverse of A times Y. That will be X, right? We know exactly. So in that case, we have exact inversion, right? So epsilon is equal to 0. A has full column rank, then X hat will be equal to A transpose Y. We have exact inversion. Okay, exact inversion. But in real life applications, it is possible, almost always the cases, that this epsilon will not be equal to 0. You have no control over A. You don't have, like, no, A can be a wide matrix to start with. Okay, it can be a totally wide, like wide matrix. Definitely it will fail the condition of it being a full column rank matrix, right? So these are the type of things that might happen in real life situations. In that case, what will we do? In that case, okay, so epsilon is random but small. Epsilon is random noise, measurement noise. So typically it is small, and no restriction or no conditions on A. On the matrix A, then this particular problem of estimation or inversion we will call approximate inversion. Okay, so in this particular case we'll go for approximate inversion. So this approximate inversion is what we want to do. Okay, so approximate inversion, and what really happens in that approximate inversion is that you will still want to minimize this ax minus y whole square, right? So this you still want to minimize, but along with that, now there are various objectives that you can attach to it. Okay, so in that approximate inversion you will still want to solve this problem. So if A does not have full column rank, then what do? You will have to still solve this problem. So you will not have a unique solution to this, but you will have multiple solutions to it. And amongst those multiple solutions now that are possible for this particular least squares problem, you want to choose one. And how do you choose one? You have some more restrictions through the cost function, right? So what those restrictions might be? So those are coming through something which is called as regularized inversion. Okay, so what is regularized inversion? So this part we will study. Okay, so this part we will study only J1. How do you find out solution? This part we will study. Okay, so through SVD we'll show all possible solutions. We'll compute all possible solutions to this least squares problem. But now you have some more interesting constraints. Okay, so one of the constraints it you might have is that norm of x square is small. So x is small. Okay, small meaning that the values of x are as small as possible. Okay, so this has something to do with you have some prior knowledge about X and you are trying to match that prior knowledge. And what was the prior knowledge? Prior knowledge about X that you have. Prior knowledge about X that you have was X has smaller values. X has smaller values than larger values. There are infinitely many solutions. You will try to find out those X which are smaller values, right? So this is one objective. Okay, J2, that this is smaller. Or you can have another objective. What might that objective be? That objective might be that it is a solution. It still minimizes this, but on top of it, it is also close to some prior vector. Okay, so X is close to a vector x prior. X is close to x prior. Okay, so this is also something that you will like to impose, saying that okay, I want a solution to this ax is equal to y, but at the same time I want this x to be as close to x prior as possible. Okay, so these are some real life applications. These are the places, some places where these type of things do come into the picture. Okay, so like one of my PhD students was working on this type of problem where this condition was required to be met. Okay, so you will be surprised to know, but this type of problems problems actually arise in something which is called as finite element model updating problems. Okay, so this is a very fantastic classical problem, and there this x prior actually has some meaning, okay, some important meaning, and you want your solution x to be as close to x prior as possible. So these are some real life problems exist where these type of regularized inversions are required, right? So these are the type of things. Other important constraint that you can have is on this dx square. So what is d? Where d is first difference matrix. Okay, so where d is the first difference matrix. So by saying that this d, how does this d really act? So this d really acts on vector x such that you get dx as entries xi plus 1 minus xi, right? So the entries of dx are basically xi plus 1 minus xi type. So what you are really saying, by forcing this norm to go to 0, you want this difference to be really very small. And when you are saying that this difference is really very small, you are asking x to be smooth. Okay, x is smooth, so there are no sudden changes in x. Okay, there are no sudden changes in x that are possible. Okay, these are the type of constraints, these are the type of additional objectives that you have. Okay, so these are the additional objectives that you have along with the primary objective that you want to minimize this j1 to be equal to ax minus y. So based on the application, so these type of smoothness conditions generally are very useful in time series modeling. Okay, so when you are doing time series modeling, in the time series modeling, you don't want these time series values, adjacent time series values. Okay, so xt and xt plus 1, right? These values, there is no big difference between them, there is no sudden jump in the time series values. Like it might be representing the stock value, right? So when you have a stock value, then what do you have? Like you don't expect that like within a minute the stock value will suddenly jump or suddenly fall down, right? It's kind of continuous. So there is a trend. That trend is what you are trying to catch through this model, possibly ax minus y whole square. But at the same time, you want that these values do not change drastically, right? They don't change drastically. They don't jump too much, xi plus 1 xi plus 2. So you want this time series to be smooth, right? So that smoothness actually is the additional objective, and that objective can be set through this dx square. Okay, so these are the different type of things that you have. So you can finally choose. So this approximate inversion, in the approximate inversion, what you can really do is that you can ask the question. So estimate x hat by minimizing. Okay, so estimate x hat by minimizing like several such objectives, right? So the basic or the primary objective is this, you want to minimize this. Along with this, you have this some other objectives that might be around, right? So this is what this is. Sorry, this is lambda k into jk. So this is what is happening, right? So one of the, so this particular inversion is regularized inversion. Okay, so regularized inversion or regularized inversion or regularized estimation. Okay, so this particular problem is of importance. Many real life situations will have this. Okay, so this is what you have. So now, so one of the important regularized inversions, very famous, is called as Tikhonov regularized inversion. Okay,
Sir, I had a doubt in regularized inversions.
yeah,
Can you go to the previous
yeah,
slide?
yeah. I'll. So Tikhonov, yeah.
Sir, in this, go to the previous slide before this. Sir, in this, how can we put conditions on X? Because X will be given to us, right? Uh,
No, x, which x is given to us?
then you're telling in regularized inversions, the
Yeah.
second norm of x square should be small. This is the
Yeah.
condition we're putting.
No, it's not condition. It's an additional objective that we want. So it is like J2. So my J1 primary objective is that I want this X to be such that Y minus AX is minimum, right? So that I will be able to estimate, or I will be able to find out the values of X through the inversion. Is that fine? The first thing.
Yes, sir.
Yeah. So now the thing is that if epsilon were equal to 0, if A has full column rank, then you know that there is only one possible exact inversion possible, right? There is only one inversion. You have a unique solution to this problem, which is given by X that is equal to pseudo inverse of A into Y. Is that okay?
Yes, sir.
You agree with this? Now the thing is that epsilon is a random measurement. It's a noise. Okay, small noise. It is random. We don't know exactly what it is. So if you don't know exactly what that epsilon is, then you will always have approximate inversion. Like you will not be able to have a unique solution to this x hat is equal to a pseudo inverse y, because this thing is actually not known to you. It is random. It is changing, right? At the same time, I can relax the conditions on A also. I will not require that A has like A has full column rank. That is the condition that we had. I'll relax that. So you take epsilon equal to 0 still, but A is not a full column rank matrix. Suppose A is square, then also we'll have infinitely many solutions X, which will satisfy this AX minus Y minimum value. This one. Do you agree?
Yes, sir. Sir, in this
Yeah.
we're going to estimate the values in A, right? So that
No, here we are still finding out values of X. We are given A and given Y. We are given A and Y. These are given to us. We are still trying to find out what is X. We are not finding values in A.
okay.
A and Y, they are both given to us. X is what we want to find out. And now you consider a situation where this full column rank condition is also not put on A. Okay. Then you can have a problem like this. A is like this, X is like this, and Y is like this. So this is your A, X, Y. That is also possible now. In our first setting of least squares, we had said that A should have a full column rank, right? A should be tall, at most square, right? In that case, invertible. Then you have a unique solution to the least squares problem. Do you remember that? But now I am
yes.
saying that that is also not required. Suppose you have a problem like this, then we will show later on when I talk of SVD, then we will show that X will have infinitely many solutions. Okay, in such a case, X will have infinitely many solutions. Okay, so on top of it, X is also measurement noise, which is random, that is available to, that is allowed to vary. So we will only look at approximate inversion. Okay, so there is no question of a unique solution X. So now, if there is no question of a unique solution X, then we can have additional objectives on X, that X be small vector, small in the sense that norm of X be small, or it be close to a prior vector, as close to possible to this prior vector as possible. So it still has to satisfy this Ax is equal to Y. What do we mean by it has to satisfy Ax is equal to Y? We still have to minimize this J1, but along with minimizing J1, we have additional objectives on X now. What is the objective? That either the X norm should be small, or X should be close to this prior vector X prior as close to possible, along with this J1, right? Or X be a smooth vector. If you have a time series interpretation in X, then X be a smooth vector, because that is what you really want. So these are different types of applications that demand different additional objectives apart from this J1, which is minimizing distance between AX and Y. Is that okay?
Yes, sir. Now
And
it's clear.
based on the importance of those objectives, based on the importance of those objectives, you will decide what are these lambda 2, lambda k, and so on. So okay, so this is your primary objective. You want this, and based on that primary objective, you will decide what is this lambda 2, lambda k, and these minimization and obtaining x hat such that these things are done is called as regularized inversion or regularized estimation. Okay, so this is what we are doing. And one particular example is that of Tikhonov inversion. So in Tikhonov inversion, what is really done is that you choose x hat. Okay, so you choose x hat. So what you really are doing is basically x hat is argument minimum over all x in Rn such that norm of ax minus y whole square plus lambda norm of x square. Okay, so this is what you are doing. So this is called as Tikhonov regularized inversion. So this Tikhonov regularized inversion is a bi-objective. Okay, this is a bi-objective, and this is what you do. Okay, yes, who was?
Yeah, sir, if you can go back to the last page.
Yeah.
Sir, so here the measurement error, the epsilon might creep in either in A or in B.
A or B? What is A or B? No. So it is going to creep only in Y. A is fixed. A is known and
Sorry,
is
I mean
fixed.
A and Y, A or Y.
No, it is not going to come in A. A is fixed. It is a given matrix of constants. So A is basically telling you how
Okay.
X and Y are related. So that relationship between X and Y is fixed. This is estimation or inversion, which is linear because I'm taking this relationship to be linear. In real life problems, many a times you have this relationship which is non-linear, which is basically Y is equal to f of X plus epsilon. This is a non-linear relationship between X and Y. You are still doing this. You know what is this F, you know what is this Y, and you are trying to find out X based on this. That's what you are doing. Okay. So whatever inaccuracies that are going to arise, they are all going to get translated to Y, because Y is what you are measuring, and that Y has this noise epsilon. F is fixed, the relationship. So A in this particular case is fixed.
Okay, so then the equation in the next page where we are writing yes, ax minus y.
Yeah.
Y inherently, does it include the epsilon? Or
Yeah, so when you have actual data given, Y will inherently have epsilon included inside Y.
yeah.
So typically when you see the real life problems, you are really looking at Y minus epsilon, basically. That is the measurement that you have. So the data that you have is Y minus epsilon always.
Okay. Okay. Thank
That's
you.
what. Yeah.
And sir, if our only objective is to minimize ax minus y, then we can use SVD. Is that correct?
Yeah, so if that is the only objective, then I will show through SVD how infinitely many solutions exist to this estimation or approximate inversion. That I will show.
Yes.
So for that I need SVD. Okay, so that's why so far if you see anytime I am talking of least squares problem, I am always talking of least squares problem with full column rank condition. But I'll relax that full column rank condition later on when I have SVD at my disposal. Then I'll show how SVD can be used to compute all the solutions, infinitely many solutions, and so on and so forth. Okay.
Sir, what we're doing here, is it related to regression, like linear regression, regularized linear regression?
Yeah, it is regularized linear regression only.
Okay, okay. No, in that we had y is equal to x beta hat plus epsilon. So that's why I was getting confused in this. In this, the
So
x is a, right?
yeah, that capital X is capital A here. This is
And
linear
beta is
algebra notation, and you are talking of typical regression notation. XY data is given, so beta is the model parameter. So that beta is small x here. Okay, that's
okay,
all.
okay.
But we are doing exactly the same, regularized regression only. So I was going to say that, but you already said it anyway. So what happens in that regularized regression or regularized least squares? We'll see.
Sir, what is the last row in the difference matrix?
Huh?
What will be the last row in this?
No, so the difference matrix will reduce the size of the vector of size n to n minus 1.
Then
So
will
it
the
will
size
be,
of J2 be different from that of J1 or
what is
both?
size of J2? They are all norms, na? They are all real numbers.
Oh, okay, okay.
You are minimizing or maximizing, na? So that has to be a real number only. So you're talking of norms only, you're talking of norms. So so the vector that you are looking at here will be an n vector. And if you see dx, it will be an n minus 1 vector, but it's eventually a norm, right? It will give you a real number only.
Actually, I got confused. There was one place where you stacked all those A1, A2. A and
So
B1, B2, Bn, but they were of same size you mentioned.
no, no. So this is what I had, right? So now you stack and you see what happens. You stack and you see what happens now. You write it down and you will realize that there is no problem here. You write it down. If you have problem, you can ask me again. But you stack all these things down the way we decided we will stack down, and you will see you can adjust it. There is not a problem. Okay.
Okay, sir.
The rows of A will change, right? M1, M2. So the D has n minus 1 rows, which is fine. It still has same number of columns. We need same number of columns everywhere, no? The number of columns is D will have n minus 1 cross n. That is the size of D. So that should not be a problem. You just write it down, you will realize. Okay. So you look at this Tikhonov regularization. So in Tikhonov regularization, if you look, then the A tilde, the stacking that we had done, you see it will be of this type, A and root lambda identity, right? A and root lambda identity. And you see here, irrespective of what happens to A, whether A has full column rank or not or whatever, this matrix A tilde will always have full column rank, right? So which implies that A tilde is always full column rank. Okay. Without any assumption on A, right? So rather than always A tilde full column rank, I have not said this officially. So A tilde has linearly independent column. That is what we have said. Linearly independent columns without any condition on A. Correct? You can see that very easily. That's true, right? Without any condition on A, this matrix A tilde will always have linearly independent columns. Can you prove that? How will you prove that? Looking at this.
Because of the property of I.
Yeah, because identity matrix is sitting there. No, you multiply vector x on the right hand side equated to 0. Then because of this identity, you will see immediately that x has to be 0. Otherwise, this equation will never be satisfied. And that's the only, right? That's the only solution that you will have. Any other non-zero vector that you put here, you will never get a 0 here because of the identity matrix sitting here. That means that there is only one vector in the null space of this matrix A tilde, which is 0 vector, which means that this matrix has zero nullity, which means that it has linearly independent columns, right? So this is very interesting argument. So what do we have here really? So what do we have here really is that x hat will be A tilde transpose A tilde inverse A tilde transpose into that vector B, right? So the B vector, I think Tikhonov regularization, did I take B or Y? Okay, so let me take a B here. That's what we will have. And what will happen then? Okay, so how will this look like? So it will look like A transpose A plus lambda times identity inverse into A transpose B. Okay, so x hat will look like this. And those who have learned regression, they would immediately recognize this particular thing, right? They will immediately recognize this particular thing. So this is something that is really very important. Okay, so this is what you have. This is what you have. One interesting example though that I want to tell, like where these regularization things really come important, is that of image deblurring. Okay, image deblurring. Okay, so what really happens is that suppose you have a vector x which is an image. Okay, so I have a matrix of the image and I just put it like column stacked one below the other, and I bring it to a big vector, right? So for your MNIST data, I think you have already done this, so you understand what it is. Okay, and what I really give you is y is equal to ax plus some noise epsilon. Okay, ax plus some noise epsilon. So what is this matrix A doing? A is basically a A is actually a blurring matrix, right? So it blurs the image. Okay, so what A is doing? A is blurring the image, and then there is some noise also that is getting added. Okay, so you have this original image. A is blurring the image, and epsilon, what is epsilon doing? Epsilon is noise. And what do you really observe? You observe this y. Y is the observed image. So what is the observed image? Observed image is blurred and noisy image that you observe. From this image, what do you obviously want to do? You want to recover the original image X, which was like without blurring and without noise, right? So that is what you really want to do. So clearly what we have here, is de-blurring problem, right? So this problem is called as de-blurring problem. It's a very important problem because this is like real life, right? This is what you will have. So why? So in real life, what happens is you will not even know the blurring matrix. But here we'll make assumption that okay, we know the blurring matrix. Okay, so this A matrix, blurring matrix is known to you. Then what will you really do? You want to have ax minus y. You want to minimize this, right? You want to minimize this, all right? But not that you want to minimize this. What do you have? So what are you trying to recover? You are trying to recover the image. So how are you recovering the image? Obviously by minimizing this ax minus y whole square. But there is some restriction on the image also. And what is the restriction on the image? So there is another objective that you are trying to match, which is like dhx whole square plus dvx whole square. So what this is really saying, what is this objective really saying? Is that, this image is such that if you look at the pixels of this image, okay, horizontally and vertically. So suppose this is the pixel that you are really looking at. Then horizontally, H represents horizontally. So horizontally and vertically, V represents vertical. So horizontally and vertically, the pixel values do not change drastically. So there is kind of continuum in the pixel values in the image, right? There is no drastic change in the image. Like the values in the pixels do not jump. So gradually the values in the image are changing. That is what you have. Typically, that is what you observe in any image, right? So this is the additional smoothing, okay, smoothness constraint that people will actually impose. So this is like your primary objective J1. So you obviously want to reconstruct or recover the image through your primary objective. But at the same time, with your secondary objective J2, what you are really asking is that the recovered image be as smooth as possible, right? So that is something that you are really interested in doing. And then you can vary the values of lambdas. And by varying the values of lambdas, you will get different things, right? So typically, like the value of lambda, you will take several values of lambdas. Okay, so suppose lambda belongs to lambda 1, lambda 2, up to lambda k. Okay, so this is something that I should not say, but I'm just saying. So suppose there are s values of lambda. Okay, s different values of lambda you try here. Then you get s different recovered images, right? X1 hat, X2 hat for those different values of lambda. And based on your application and based on your experience and all, you choose the best value of lambda that suits you well based on the data that you see and so on and so forth, right? So this is like lambda. How do you choose lambda? Based on your prior experience and playing around with this data, right? So these are called as paths, okay, different paths. So each lambda value corresponds to a path in this optimization, and along these different paths, you are trying to find out the minimum values. So along different paths, you get different minimum values and you choose those values. Okay. So this is like going too much into optimization that I really don't want to go at this point of time, but this is what is really happening. So is this image deblurring thing clear to all of you? Like what these DH and DV operators are doing, they are actually trying to find out the horizontal and vertical differences in the images, consecutive pixel values, and by having that as your secondary objective, you are actually forcing the recovered image to be as smooth as possible. So the image is primarily recovered because of J1, and J2 is ensuring that you have smoothness in the image. Okay, so that is what you see. Okay, interesting applications of this. So yeah, just
sir, in the previous slide,
yeah.
Sir, when you're optimizing J2, in the borderline of an image, there will be sudden jumps, right? I'm not understanding why
Yeah,
does
so everywhere the smoothness will not be there, but like image will be recovered, right? That's why it is your primary objective, that you have to recover image. So there were sudden jumps, then you cannot avoid them, but as much as possible try to avoid sudden jumps. Majority of the places the image will be smooth, right? So that's what this thing is imposing.
Okay,
That's
okay.
all. Yeah. So this is something that is, I understand, too much of hand waving going on. Unless you really work some examples, you really see what is happening, you will not realize. And then again, these parameters, lambda and all, that you have to choose them. Like I was explaining here, you have to choose various values of lambdas, and for those lambdas, see how the recovered images look like. Based on that, you will choose what is the value of lambda. So there is a lot of like hand waving and things are going on. But at the same time, there is this least squares coming into the picture, right? So this least squares is like through Tikhonov regularization, or in general these things that I was talking about, right? So that's the least squares connection to these problems. That's what I just want to point out.
Sir, one question. The blurring matrix, that is something we don't know, isn't it?
No, sometimes you know that is there. Sometimes you know how the blurring is there.
Okay.
Yeah.
Okay.
Sir, this Tikhonov, this one, that part, is it same as ridge regression?
Yeah.
It's the same, right?
Yeah.
Okay, sir.
So you will see why it is ridge regression. The next point I'm going to talk about is that point only. So once I write those next 2 pages, then you will be able to map it to that ridge regression thing that you're talking about. Aviraj, do you have to say something? You have doubt?
Yes, sir. So we used the weighted sum method to convert the multi-objective optimization problem into a single objective optimization. Is there any specific reason why we use this particular scalarization method and not something like fuzzy method or some other method?
No, because I am just trying to show that this is one possible way of solving this problem.
Okay.
I want to relate it to linear algebra and least squares. That's why I'm doing it. Okay.
Okay.
Yeah, because it naturally fits that linear algebra thing, right? It naturally fits my like formulation that I already had.
Yes, sir.
Yeah. So the next thing I want to talk about, like next application, is like in that of regularized data fitting. Okay, regularized data fitting. So in the regularized data fitting, I'll not go too much into it, but this regularization actually helps you in a way try not to overfit. Okay, not overfitting. So not overfitting is bad thing. I'll say if you do regularized data fitting, then regularized data fitting actually avoids overfitting. Okay, so that is roughly what it is doing. Though I will not go into those details because we have not like really said what this regularized like overfitting thing is and so on and so forth. But I'll just tell you like what is happening is this regularized data fitting. Okay, so I hope you all remember the terminology. So f hat x was the model. And how are we obtaining this f hat x? Alpha 1 f1x plus so on so forth up to alpha p fpx, right? Where f1, f2, fp were the basis functions. They all were functions from Rn to R, right? So that's what we have. And then what is it that we are trying to find out? We are trying to find out alpha 1, alpha 2 up to alpha p, right? And they are found out using that least squares objective function. That's what we were doing in the data fitting problem. So this is our data fitting problem. Now what is regularized data fitting problem? So first let us try to understand the alpha 1, alpha 2, alpha I. Okay, so we can interpret what these alpha i's are. Okay, so roughly we can interpret alpha I as the amount by which our prediction depends on Fix, okay, the ith basis function. So if theta I, so suppose this alpha I, this parameter alpha I, so if alpha I is large, then it will the prediction will be very sensitive, right? The prediction will be very sensitive to small changes in Fix and this will be particularly true in case of unseen data. So what are we going to do? So suppose X is the unseen data, it is the test data, right? So suppose X were test data here. Okay, so X is test data. Because there are small changes, small perturbations in test data, that may result in a very large perturbation in your prediction because alpha is really large, right? Because alpha will magnify that, it's large. So small changes will magnify, and that is something that we try to avoid in overfitting. Okay, again, this is very hand waving. It may not be clear to many of you also. I'm not saying I am explaining it in a very nice way, but this is something that you definitely want to avoid, right? Small change in Fix will be magnified because of this alpha is very, very large, right? So in the prediction, it will have a bad effect. So you can have an additional objective. What is the additional objective that you have? So first you want to fit the data, obviously. So you have your primary least squares objective function. What was that primary least squares objective function? It was y minus a alpha, right? So alpha is a vector of parameters. Alpha 1, alpha 2 up to alpha k, right? Alpha 1 up to alpha k. That is your primary objective. But after that primary objective, what you can ask for is that norm of alpha be as small as possible. So if you ask for norm of alpha also to be as small as possible, then each individual alpha automatically becomes smaller. So the smaller the alpha is, it will be the prediction will be less susceptible to changes compared to small changes in Fix, right? That is something that you can have. So that is the regularization that you are enforcing, and by enforcing that regularization, what you are doing, you are making your prediction less sensitive to the small changes in Fi. That's what you are doing. Of course, if Fi changes like drastically, the prediction also needs to change drastically, right? So ideally you will want changes in Fi to get reflected in changes in y hat, the prediction. That's what you are trying to understand. But small changes in Fi, you don't want to see suddenly very large changes in the prediction. That's the reasonable assumption typically people make. And that is what you are enforcing by this secondary objective, right? So that is the regularization that you are doing. So this is the regularized data fitting. The only place where this will happen is that if the basis function were constant one, then you do not really care like what happens to this alpha, whether it is small or large. This basis function will always be constant, right? So then you don't really worry about it. And then if you see it from that point of view, then this is basically nothing but ridge regression, right? Those who would have done ridge regression course will immediately recognize that that's what I'm really doing, right? So what I'm really doing in like regression notation. Okay, those who have not seen regression, please don't worry about it, because now you understand it, and when you do regression course after this, you will connect this the other way around. But those who have already done regression, I'll just write down in regression notation what they have done. So y minus x transpose beta minus beta 0, right? Square plus norm of beta whole square. That's what you had done, right? You have minimized over all possible betas and you find out beta in such a way that this is what is happening. So if you want to call it, you call it beta 1, and beta is basically beta 0, the constant, and beta 1, x1, x2, which depends on the covariance x, right? So this is something that you have seen already in regression. This is like your ridge regression, right? You call this ridge regression problem. So this regularized data fitting, basically when you choose basis functions appropriately and all, you are basically doing ridge regression. Okay, so that's what you are really doing. So these are the connections. I think this is all I wanted to say about this. This is all I wanted to say about this. What it is called, multi-objective or bi-objective in particular, multi-objective or bi-objective least squares problems. Is that okay? Like roughly, do you get the idea of what is really happening? You'll have to go through it again, and I would really tell you that you please read chapter 15 and chapter 16 for the next topic that I'm going to say. So please read chapter 15 and 16, 17, these three chapters from the book Applied Linear Algebra. And I think least squares. What is the title of the book? Introduction to Applied Linear Algebra, Vectors, Matrices, and Least Squares, right? So vectors, matrices, and least squares. Okay. So these three chapters very nicely from Stephen Boyd book. Okay, so this book is available on website of Professor Stephen Boyd, Stanford University website of Professor Stephen Boyd hosts this book. You have a complete PDF available for you to download. I had already told this. So please go to his website, download this, and actually like read these chapters. So today what I'm covering basically comes from these three chapters, 15, 16, and 17. And least squares data fitting and least squares classification comes from 12, 13, 14. Okay, so chapters from 12 onwards, they are really very like interesting chapters. Unfortunately, I'm not able to cover everything that is given in those chapters due to time constraint, but you will realize that those chapters, like amazing description, beautiful examples, and very nice explanation, like probably 10 times better than what I'm doing in here. If you read that book, you will realize that that explanation, like such a wonderful style of writing that book. These things will become like very clear to you. Okay, so I'll give some assignment problems and this explanation that is there in the book together. Everything, if you do, you will understand everything that is really happening. Okay, so please, my sincere request to all of you to go back to that book and read those chapters from book, like word to word. Amazing description. There will be many things that will become clear to you. Okay, so please try to do that. Okay, so that is something that I definitely want you to do. So this is what I wanted to say about multi-objective least squares. And there is another topic that I want to cover, that is of constrained least squares. Okay, so constrained least squares. So this is something that I want to do. So typically what is happening in constrained least squares problem? So you are getting the least squares problem, minimize this norm of ax minus b whole square. That is what we are minimizing, subject to the constraint that cx is equal to d. Okay, there is a constraint now. Constraint is that subject the constraint that cx is equal to d. Okay, so x is a variable that we want to find. So this is called as objective function. This is called as objective function. This is called as constraint. Okay, this is called as constraint. And what really happens is this is a linearly constrained least squares problem. Okay, the constraint is kind of affine here, so this is called as linearly constrained least squares problem. So least squares because the objective function is least squares, and linearly constrained because the constraint is affine or linear. Okay, so that's why this problem is called as linearly constrained least squares problem. And like there are many constraints. I have put those constraints together in the matrix notation. So basically, if you look at it, this is the matrix C. This is your vector X is equal to D. This is the vector D. Then you can see that the many constraints on the variable X are basically you take the row of C, multiply it with X, and then you get this value of D. So this is ith row. Then this is the ith value, right? So that is what you get. So Ci transpose into X is equal to Di. That is one constant. There are several linear constants like this. I put them together in the matrix notation to get one constant. In the matrix form, Cx is equal to D. Okay, so that's what is done. And typically there is a terminology that is used. So feasible solution basically is a solution X in Rn. So feasible solution is a solution which is X in Rn, which satisfies the constraints. Okay. So any vector in Rn which satisfies the constraints is called as feasible solution. And once you have a feasible solution, you choose the optimal solution from the set of feasible solutions. So what is the optimal solution? Optimal solution or optimal point is the optimal solution X hat in Rn is such that first condition X hat is feasible. That means that it actually satisfies all the constraints. And the second thing is that norm of Ax hat minus b is less than or equal to norm of Ax minus b whole square for every x in the feasible set. Okay, what is the feasible set? Feasible set is set of all vector sets which are feasible, right? So that's why that's what we want. So such a solution X hat will be called as optimal solution. And what we want to do, we want to find out the optimal solution, right? So this is something that we want to do. Many of you would have seen this problem in optimization earlier. You would have seen that whenever you have constraint, you do least like Lagrange multiplier, right? And when you do Lagrange multiplier, excuse me, when you do Lagrange multiplier, you see something like norm of Ax minus b whole square plus lambda into Cx minus d, right? Something like that you will see. So this I can write down in terms of norms also, Cx minus d, I can write this down. And then this becomes like, is this a multi-objective problem now? So it actually is multi-objective problem. So the connection between these two problems is that consider this bi-objective problem. Consider the bi-objective problem, which is this. Okay. Then as you let lambda to go to infinity, the solution of this multi-objective problem, the solution X hat of this multi-objective problem. So I'll X hat, okay, of this star converges or tends to the linearly constrained least squares problem. Okay, so double star converges to X hat linearly constrained least squares problem, LCLS of star star. Okay, so that is the relationship. So practically what you will really do, is you let lambda to be a very large number. Okay, so lambda is like 10 power 10 power 15, something like that. So if you let lambda to be a very large number and solve this bi-objective problem, then whatever solution you get to this bi-objective problem, that is the approximate solution, or the solution is close to the constrained least squares problem solution. Okay, so that is the connection between the bi-objective least squares problem and this constrained least squares problem. Okay, so that there is because of this connection between these two problems, many a times people kind of make confusion. Okay, people kind of are not sure like what you are exactly doing. But one thing that you have to understand is that in the bi-objective problem, the star problem that I have written, you have to see I am minimizing norm of Ax minus b whole square plus lambda times norm of Cx minus d whole square. Okay, it is not necessary that this cx minus d whole square term will go to 0. Right? I will have a compromise between the two objectives J1 and J2. J1 plus lambda J2 is the compromised objective cost function, and I'll have compromise, but I cannot say for some value of lambda I'll have this cx minus d actually equal to 0. The norm of cx minus d actually equal to 0. One thing that you have to understand here is that constraint least squares problem demands that cx has to be equal to d. The constraint has to be satisfied. When you are saying constraint has to be satisfied, you have cx is equal to d. That means that norm of cx minus d is actually equal to 0. So you see, now you understand when I let that lambda to be a really very large number. If I have that lambda to be really very large number, what am I really saying is that in order to minimize this star, this cx minus d really has to go to 0. Right? That's what I'm really saying. So by forcing this lambda to be a really large number, I am forcing that cx is equal to d is satisfied. So that is the connection. Okay, so that is why if you let this lambda to really go to infinity, the solution will actually be same as the solution of linearly constrained least squares problem. But fundamental difference, you cannot just arbitrarily choose some lambda and then you say that, okay, these two problems are same. Bi-objective problem is same as constrained least squares problem. No, because in constrained least squares problem, you see, what are you calling it to be a solution? First, x hat has to be feasible. What is feasibility means? Feasibility means that cx is equal to d, the constraint has to be satisfied exactly. Okay, first the constraint is satisfied, then you look at all the vectors which satisfy the constraint, and then you choose that x hat which will minimize the cost function ax minus b whole square. That is what you are really doing in this constraint least squares problem. So this cx minus d whole square really has to be equal to 0. So how do you connect it with the bi-objective problem? The way you connect it to the bi-objective problem is that you take this lambda really very high. So if this lambda is really very high, like 10 power 15, then this should be really very small in order that you will be able to minimize this star function, right? So roughly that is what you are asking, that you can actually show analytically, but all those calculations, analytical calculations, we are not good, right? So that will kind of ensure like within the acceptable bounds, cx is equal to d is satisfied, right? So you have to set up tolerance and so on and so forth. But that is basically the connection between the bi-objective problem and constraint problem. Is this clear? So you will see these type of problems often, like people will switch and they will make very loose comments like lambda इधर डालोगे तो constraint बन जाएगा and all those type of things like people say. But I think this is not as straightforward as it is. You have to understand this really very well in order to like see the connection. Okay, so I hope this point is clear. The constraint least squares problem is clear. The connection of constraint least squares problem with bi-objective problem is also clear. Is that okay?
So this is essentially the same as using Lagrange multiplier plus KKT optimality conditions, right?
Yeah, so we will come to that. Lagrange multiplier and KKT optimality conditions will actually come to that. And if there is time today, then I will actually prove those Lagrange KKT conditions for this constraint least squares problem. Today we'll write those expressions down if I have time enough. Okay, but you are right. Basically, that is what it is. And that's why this connection with the bi-objective. Is that okay? Yeah. Okay, so the first thing first, like where such a thing will arise. Okay, so let us take the example. So the example where least square constraint least squares problem arises. Okay, so basically it arises in something which is called as piecewise polynomial fitting problem. Okay, piecewise polynomial fitting problem. So what we really do is we want to piecewise polynomial fitting. Okay, so pictorially, so this is a picture which is I'm taking from the book. So there are data points here. So these are the data points you see, and I want to fit okay, I want to fit a polynomial to these data points. Okay, so these are the data points I have, and because you see I have used two different colors, you can guess that two different polynomials are being fit. So on the green points up to the point A, I'll fit one polynomial, and after this I'll fit another polynomial, And what is really happening? At this particular point, something is happening, right? Those two polynomials are joining, and where those two polynomials join, I have certain conditions on those polynomials, right? So those conditions basically will get transformed into this Cx is equal to D. So the conditions that I'll have on those polynomials at this point A where they meet, those conditions will be that first, the two polynomials should meet each other. So I'll have a continuity condition. Then I'll have a smoothness condition also, that both these polynomials first derivative also should match at this particular point, and so on and so forth, right? So I'll have conditions of this type imposed on those polynomials when they meet at this particular point A. And such a piecewise polynomial fitting problem, these polynomials spline fitting. Okay, so this is a problem that arises naturally in polynomial fitting. Okay, they are called as splines. It's very useful. Okay, so that's what we have. Okay, so in the notation f hat x. Okay, so f hat x, our model f hat x, the model is basically equal to one polynomial px, where x is less than or equal to a. So in this region you have this polynomial which is px, and in this region x greater than a, you have another polynomial, let us call it qx. Okay, so this green polynomial is basically qx. So this is what you want to do, and this is how f hat is defined. And what are these polynomials p and q? So p and q, px and qx are polynomials of degree not more than 3. Okay, so basically they are degree 3 polynomial with degree less than or equal to 3. No, degree less than or equal to 3. Okay, so what these polynomials will look like, basically the polynomial px, let us say it looks like alpha 0 plus alpha 1x plus alpha 2x square plus alpha 3x cube. Okay, this is how the polynomial px looks like, and polynomial qx will look like, I'll use the same alpha because it will become easier for me. So alpha 5x plus alpha 6x square plus alpha 7x cube, right? So that is, did I make a mistake somewhere? No, alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, right? So this is how these two polynomials are. And what do we want to do? Of course, we want to compute best choice of alpha 0 up to alpha 7. And how will you choose this best choice? So the best choice will be chosen based on data. So what is the data that is given to us? So the data that is given to us is x1 up to xn, the points in R, and correspondingly y1, y2 up to yn, the points in R, which are the values of the function x, right? So the pair xi, yi is sitting here. So this is a typical pair xi, yi, right? So the points on x, xi's are here, yi's are here, and the point xi, yi typical point is this particular point. Like that, capital N number of points are given to us. And how will we choose this? How will we choose this? So this is something. Okay. So what is the condition at A? So what is condition at A? Condition at A says that the polynomials at this point should be continuous, and first derivative also should match, right? So how will I write this down? Okay, so the way I'll find this out, is the following. So let us say x1 up to xm. So let us say these points. Let x1 up to xm, x1, x2 up to xm. These are the points which are less than or equal to a, and xm plus 1 up to xn are the points which are strictly greater than a. That's how I arrange the points and I name them. Okay. Then what am I really doing at? So what is the prediction error? So the prediction error is the following, right? So let us write down prediction error. So the prediction error is this. What is the prediction error? Summation I from 1 to capital M, alpha 0 plus alpha 1 x plus so on, So there is nothing much I can write down. Alpha 2 x square plus alpha 3 x cube. That is the polynomial px, because before m to the left of a, so up to point m you have polynomial px. So what is happening? Alpha cube. So I have to be a little more careful when I'm writing this. So this is I, and I will square this, and this is ith data point. I'll cube this minus yi, correct? I'll take square of this. So this is the sum of prediction errors for the polynomial p. And similarly, what will be this? I is equal to m plus 1 to n, and you will have alpha 4 plus alpha 5 xi plus alpha 6 xi square plus alpha 7 xi cube minus yi, right? The square. So this is what you will have coming out of polynomial this. And what is the condition? The condition, another condition that you have. What is the condition? Continuity. Okay, continuity at A means that PA has to be equal to QA, which basically means that PA minus QA has to be equal to 0. And what is the other condition? The other condition is that smoothness. So what is smoothness at A saying? Smoothness at saying is that not only the function values match, but their first derivatives also match, which implies that P dash A minus Q dash A is actually equal to 0. Correct? So what are the conditions? What are the conditions that you have? The conditions, these two conditions, okay, continuity and smoothness. Okay, so let us see what does continuity really tells us. Okay, so the continuity at A, what is it telling? It is telling that the two values should match in the value. Two polynomials should evaluate to the same value at the point A. So point A is basically the point that is given to us. So you have alpha 0 plus alpha 1a plus alpha 2a square plus alpha 3a cube minus alpha 4 minus alpha 5a minus alpha 6a square minus alpha 7a cube is equal to 0, right? And what is the smoothness condition similarly saying? So smoothness condition, I am taking derivative of these polynomials and evaluating them at A, x is equal to A. So you tell me if this is true. Alpha 1 plus 2 alpha 2A plus 3 alpha 2A square. Is that correct? And minus I have what is the second polynomial? Alpha 5 minus alpha 5 minus 2 alpha 6a minus 3 alpha 7a square is equal to 0. Is that condition correct?
Sir,
Yes.
the x would be 3 alpha 3a square.
What is 3 alpha 3? Here 3 alpha 3a square. Here. So this is the smoothness condition, right? So if I write down these conditions in the matrix ABCD, okay? If I write these conditions down in the matrices ABCD, so let me define the matrices. Okay, so suppose I define the matrix C to be this matrix. Okay, 1a square a cube minus 1 minus a square minus a cube. Okay. And then the second row is 0, 1, 2a, 3a square, 0, minus 1, minus 2a, minus 3a square. Okay. And suppose I define D to be equal to 0, 0. So what is this matrix? This is a matrix is in R2 by 8. This is a matrix in R2 by 1. Correct? Is that okay? Do you understand how am I getting this matrix? I am looking at this and I am getting the first row. I am looking at this and I am getting the second row. The right hand side is 0, 0. That is coming here as 0, 0. Is that okay? And similarly, if I define matrix A and B as follows. So define matrix A. So matrix A is equal to 1, then your point x1, the Vandermonde matrix, then you have x1 square, so on so forth. So actually there is no so on so forth, I just have to write x1 cube, and then you have 1 2 3 4 zeros. So how many such rows you will have? You will have such rows up to xm, right? So 1, then the point xm, then the point xm square, then the point xm cube, and 0 0 0 0. Then you'll have 0 0 0 0 1 xm plus 1th point, xm plus 1th point square, and xm plus 1th point cube. You understand this matrix? 0 0 0 0 1 xn, xn square, and xn cube. So this is a matrix. What is the size of this matrix? The size of this matrix is n cross 8, because there are 8 parameters: alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7 that I want to calculate. Do you understand how I have written this matrix A, all of you? Is that okay? And the matrix B, what is the matrix B? The matrix B is obviously y1, ym, ym plus 1 to yn, right? So this is a vector of size capital Rn. And what is the problem that I am solving now? The problem that I am solving is minimize norm of A alpha minus B square subject to the constraint that C alpha minus D, or C alpha is equal to D, where what is alpha? Alpha is equal to alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, right? So these parameters, the first 4 parameters are corresponding to the polynomial Px. The second 4 parameters are considered polynomial Qx, right? 0, 1, 2, 3, they correspond to 0, 1, 2, 3, they correspond to Px. And this 4, 5, 6, 7, they correspond to Qx. And this is how you will compute. So this is the constraint least squares problem that will naturally arise in data fitting when you have these conditions. Is that okay? Do you understand what I have done here? Any doubt about these things? Okay. So one particular case of this particular problem that arises is the least norm problem. Okay, a particular case is the least norm problem. And what is the least norm problem? The least norm problem is to minimize norm of x square subject to the constraint that Cx is equal to D. Subject to the constraint that Cx is equal to D. So what you are saying, you are looking at all feasible solutions first, right? So what are the feasible solutions? Feasible solutions are those solutions which will satisfy this constraint Cx is equal to D. So you collect all the solutions of Cx is equal to D, exact solutions of Cx is equal to D, and then what you are saying? You are saying that Cx is equal to D solutions, you find out that x which is of the least norm, okay, which is of the least norm. So this is least norm problem. So you choose that solution of Cx is equal to D which has least norm. So you can pose this problem as constrained least squares problem, right? So what is A and B here? A is equal to identity and B is equal to zero matrix in particular, right? So in this particular problem, this is what you have. A is equal to identity and B is equal to zero. And you solve this least squares problem. One variation of this particular problem, no? One variation of this problem, okay? That is something that you will find at many places. It is not least squares, okay? That's why I am saying not least squares, okay? Not least squares, but I will change this. You are seeking minimum norm solution of Cx is equal to D. So instead of looking at two norm, if you look at this particular norm, one norm subject to constraint that Cx is equal to D, then this particular problem actually comes in one of the most important applications nowadays, dictionary learning and sparse representation. Okay, dictionary learning and sparse representation. Okay, so this is the area where this problem comes in. So when you are seeking the least norm solution x1, so this actually C that you see here is like dictionary. So this dictionary is given to you, and with respect to dictionary, can you find the sparse representation of this given data point D? That's the question you are asking. Okay, so in that terminology, this problem actually comes, but it comes with one norm. Okay, so it is one norm. So sparseness is related with this one norm. Okay, so that is what they do. Here we are not looking at this. We are not doing this problem because we are not considering one norm. We are considering two norm. Okay, so the least norm problem that we are going to solve, it will have a very nice closed form solution, whereas this particular problem also will have a solution, but the solution technique to this problem is different, and something which is called as orthogonal basis pursuit or something like that. Okay, so these are the type of variations of this least norm problems that you will see also have applications. Okay, but because we are talking of least squares, always a very nice linear algebra framework is available for us. We are always considering two norms. But when you change two norm to one norm, there is a difference, huge difference, and huge set of new applications that arise. Okay, but this is something that I really would not stop myself from saying, but please do not confuse this with anything that we have done, because it is with one norm, and what we are doing always is with spectral norm. So far in least squares, we are always dealing with spectral norm. No other norm is considered. Is that okay? So this is a very beautiful area. This is very interesting things, the interesting applications. Unfortunately, not in the realm of our course yet. Okay, so that's what I will like to say. Anything that you want to say here at this point? Anybody has doubt? Hasita, do you have any doubt? Hasita, do you have any doubt? Okay, I think she's not in the class. So how do we solve? Okay, so solution to the linearly constrained least squares problem. Okay. So similar calculations I have already done, so I'll not like spend too much of time in this. So what are we going to do? We are actually solving this ax minus b whole square. That is what we are interested in doing, subject to the constraints. So those constraints I'll write one by one. Ci transpose x is equal to di, I is equal to 1 to up to p. There are p constraints here, and those p constraints, instead of writing them in terms of matrices C and D, I am writing them individually, right? So here that Ci transpose actually ith row of the matrix C, correct? Ith row of this matrix C. So this matrix C is obviously matrix in P cross N, right? So there are P constraints, so P rows, and N is the size of this vector, right? So that's what we have. So what we will do is we will apply the Lagrange function. Okay, so we form the Lagrangian function. So the Lagrangian function is the following, right? So that Lagrangian function is a function of two variables x and z. And how many Lagrange variables will be there? The Lagrange variables will be p, right? z1, z2 up to zp. So what will we have? We'll have ax minus b whole square plus z1 into c1 transpose x minus d1. The first constant, that z1 is the first Lagrange multiplier. Then z2 C2 transpose x minus D2, that's the second Lagrange multiplier, and then this is ZP, so CP transpose x minus DP, right? So this is the Pth Lagrange multiplier. So where Z is equal to Z1 up to ZP is the Lagrange vector of Lagrange multipliers, right? So this is what you have. And what do we do? What do we do is we differentiate this Lagrange function with respect to x and z, equate that to 0 and eliminate z from that, and you get the solution x, right? That's what Lagrange multiplier methods really does. So let us try to do that. So let x hat be the solution. So let x hat be the solution to the constraint least squares problem. Constraint least squares problem, and let z hat be the set of Lagrange multipliers that satisfy. So you'll write down those gradient equations, right? So del L by, so suppose, yeah, this is the L, the cost function. So del L by del xi at x hat z hat is equal to 0 for I is equal to 1, 2 up to n. So you'll take derivative of this with respect to each component. And the other condition that you'll have is that del hat at del zi at x hat z hat will also be equal to 0 for I is equal to 1, 2 up to p, right? So by this differentiation you'll get some information, and this differentiation is only going to give you all the constraints back, right? So this is what really happens with this, right? So differentiating with respect to zi will give all the constraints back. So you can just quickly verify this is actually equal to Ci transpose x hat minus di is equal to 0, correct? For I is equal to 1, 2 up to p. You are of course evaluating at the point x hat and z hat, so that's why I wrote down x hat. And what happens for this, you find out. Okay, so what happens at this particular point, x at z at the ith derivative, I'm just writing, you look at the equation. So I have norm square, so that norm square I am writing, I have done similar calculation earlier, so I am not doing this calculation again in full details. Xj hat minus 2a transpose b I, right? So this is what I have done this calculation earlier. And then the second part is for the constraint. So you see j from 1 to p, zj hat into cj at ith component is equal to 0, right? So this is what you'll get. So these equations, if you rewrite in matrix form, so in matrix form, how these equations really will look like. Okay. In matrix form, these equations look like 2a transpose a x hat minus 2a transpose b plus C transpose Z hat is equal to 0. So these equations are giving you more information than what we typically had obtained earlier. So if Z hat is not there, then this part is corresponding to the normal equations part that we have already derived, right? So that is that first calculation. And the second term is basically coming out because of the Lagrange multiplier. This is what you are getting. So if I combine these equations together, so these and these, if these equations are combined together and all written in the matrix form, you see what I'll get. So I'll get 2A transpose A, C transpose C 0 into X hat Z hat will be equal to 2A transpose B and 0. So you see the first equation, when you differentiate with respect to xi, in the vector form is given like this. So that equation you will see is here, right? So this 2 times A transpose B is being sent to the right hand side. This is 2 times A transpose B on the right hand side, you see here, right? And the second equation is just Cx hat is equal to 0, right? So sorry, I'm not 0, I have to write down as D, right? So that is the constraint. So the second equation is just satisfying constraint Cx is equal to D, right? So that is differentiation with respect to Z hat. So these equations are actually called as KKT equations. So these are the KKT equations. So Krish Kun Tucker, okay, Karush Kun Tucker, they are the mathematicians who actually derived these conditions, not for these, but in general for convex optimization, okay, constraint convex optimization. So these are called as KKT condition. And obviously, you want this particular matrix, okay, so this particular matrix is called as KKT matrix. Okay, so we'll call this matrix KKT matrix. And KKT matrix should be invertible, right? So once you know that KKT matrix is invertible, only then you can find out this X hat and Z hat, right? So KKT matrix needs to be invertible, and invertibility of KKT matrix. Okay, this is something that I'll not do. I'll just leave it. If you want, you can see chapter 16 of this book. So invertibility of KKT matrix is equivalent to this particular fact that this stacked matrix AC is full column rank, or it has linearly independent columns. Okay, AC has linearly independent columns. Okay, so if the columns of this matrix A and C are linearly independent, then the KKT matrix is invertible. And once you know that KKT matrix is invertible, how will you compute the solution? The solution then can be computed as 2A transpose A, C transpose C 0 inverse into 2A transpose B and B. Okay, so this is how you will compute the solution to the constrained least squares problem. Okay, so this is how you compute the solution. So this is what I wanted to say about constrained least squares. The application I already talked about, where you have to have those spline polynomials computed. Is that okay? Do you have anything to say here about this? So the only thing that I have not done here, I don't have enough time to prove this, is that this condition, right? Invertibility. When will this KKT matrix be invertible? So that small part you can actually read from the book. Okay. Anything you would like to say here? Anything you would like to add? So there is a lot that has been covered today. It takes time to digest. Okay, so I will sincerely request once again to go through the book and read those chapters really very carefully. You will really enjoy reading those chapters and you will learn many things from them. Is that okay? Do you want to say something here?
So from here we'll get the values of X and Z.
Correct. So we are interested in X hat values. So X hat values you can get from here easily, right?
Yes, sir.
Yeah. So basically we want values of X hat, but X hat and Z hat together has to satisfy this. So There are computational methods. Using those computational methods, again, least squares, like you have gram matrix and you are doing inverse. So typically you will not like to do the inverse. So what will you do? So you do QR decomposition of A and C together. So if you do the QR decomposition of this particular matrix, then that QR decomposition will actually give rise to this particular solution that you are trying to compute. Okay, so that's what is being done typically. In order to compute it efficiently, the closed form solution is given in this particular form. Is that okay, Aditya?
Yes, sir.
Okay, so if there is no further doubt, maybe we can stop here today. And from the next week onwards, we will start looking at those decompositions. Okay, so we'll start with eigenvalue, eigenvector decomposition, singular value decomposition, and we'll try to come back to these concepts again, relate those concepts in the light of SVD and eigenvalue, eigenvectors. And then we'll also talk of things that will come out of that. So low rank approximations and low rank approximations and principal component analysis, right? So these are the things that we'll cover based on those decompositions. And when I'm talking of eigenvalue, eigenvector, I'll also try to do this page ranking, Google page ranking. Okay, so that's what we will do in coming weeks. So that's the agenda for next week onwards. Okay, thank you. See you in the next week.
Thank you, sir.
Yeah.